In our last video, we actually solved two questions to explain the basic concept of mutually inclusive events. And in today's video, we are going to be solving more questions to help us understand more when it comes to the concept of mutually inclusive events. And as you can see, we have three questions right here. So we are going to be going about those three questions one at a time. So let us start with the first question that says, what is the probability of spinning a prime number or an odd number on a spinner numbered 1 to 8. So the experiment right here is us spinning a spinner, and we realize that we are interested in just two events from this experiment, that is the event of having a prime number or the event of having an odd number. So the first step is for us to list out the sample space of the experiment, and it was stated that the spinner was numbered 1 to 8. So that means the sample space of this experiment is given as, also we have S, which represents the set of the sample space. We have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7, we have 8. So the next step is for us to list out the event of a prime number and the event of an odd number. Please note that a prime number is a number that has just two factors, that is 1 and itself, and an odd number is actually that number that is not divisible by 2. Taking a closer look at the sample space, we can see that we have the following prime numbers, so we can decide to write this as prime numbers. So what are the prime numbers right here? We have 2, we have 3, we have 5, and we have 7. So these are the prime numbers we have in this question of ours. And the next event we are paying attention to is the event of an odd number. And how many odd number do we have here? So we can just write this as odd, which is ODD. We have the odd number right here. So the odd numbers we have right here, we have 1, we have 3, we have 5, and we have 7. So we have 4 prime numbers and we have 4 odd numbers. If we take a closer look at the events of both prime numbers and odd numbers, we can see that there is actually a form of intersection between them. That is, some elements actually coexist between the two events. And these values are, we have prime number intersection odd numbers, and we can see that the intersection is going to be equals to, we have 3, we have 5, and we have 7. So since we have an intersection that is a common element between these two events, it simply implies that both events are actually mutually inclusive. That is, they can coexist within the same experiment. So one of the best ways to understand this is to use the concept of Venn diagram to pictorially represent our data set. So I'm going to be drawing the first circle. So we have one circle right here. So we are going to copy this circle and paste it. So we have another circle right here. So we paint this red, and then we draw our rectangle, which represents the universal set, and we make the rectangle black. So this is the Venn diagram that represents this experiment of ours. So we have here to represent the prime number, which is Pn, and we have this side right here to represent the odd numbers, which is Od. So that being said, let's try to represent the Venn diagram with the necessary details. So for the intersection, we have 3, we have 5, and we have 7. And for the prime number, we have 2, 3, 5, 7, and we already have 3, 5, 7 right here inside the prime number, so we can just write 2 right here. And in the odd number, we have 1, 3, 5, 7, and we already have 3, 5, 7 present, so that means right here we are going to be having just 1. And this is the Venn diagram that we can use to pictorially represent the question given to us. According to the addition rule of two mutually inclusive events, the formula is probability of A or B is actually equals to probability of A plus probability of B minus probability of A intersection B. So that means the probability of having a prime number or probability of having an odd number, which is ON, is going to be equals to probability of having a prime number plus probability of having an odd number minus probability of having a prime number intersection having this odd number. So this is ON, and we have ON right here also. So let's just erase this a bit, and we have our N right here. So this is ON. All right, so probability of having a prime number is actually equal to the number of prime numbers we have in the event divided by the total number of sample space. So probability of having a prime number is equals to how many prime numbers do we have? We have 2, 3, 5, 7. That is equals to 4 divided by the total number of sample spaces actually equals to 8. So that means 4 over 8, which is equals to 1 over 2. So the probability of having an odd number is actually equals to the number of odd numbers we have in the event divided by the sample space, and that is also equals to 4 divided by 8, which is equals to 1 over 2. And the probability of the intersection, that is prime number intersection the odd number, that's going to be equal to the number of intersection divided by the total sample space. And as we can see, the intersection between the prime number and the odd number, we have just 3 of them, which is 3, 5, 7. So we have this to be 3 divided by 8. So the probability of having a prime number or an odd number is going to be equals to 1 over 2 plus 1 over 2 minus 3 over 8. And when we use our calculator to do the mathematics, we have our answer to be equals to 5 divided by 8. When we convert this to decimal, we have the answer to be 0.625. So we have a 62.5% chance of having a prime number or an odd number if we have a spinner being spinned. So let's move to the next question. So the second question says that 2 fair die are rolled on the board. What is the probability of getting a sum less than 7 or a sum less than 5? So the first step is for us to get the sample space when we have 2 fair die rolled at the same time. So I'll be sketching that as fast as possible. So we have one horizontal line right here, and then we have another horizontal line right here. So the sample space of the first die is we have 1, we have 2, we have 3, we have 4, we have 5, and we have 6. And for the second die, we have 1, we have 2, we have 3, we have 4, we have 5, and we have 6. Please note that the question was interested or is interested in the sum of the outcome of both die rather. So that means 1 plus 1, that gives us 2, 1 plus 2, that gives us 3, 1 plus 3, that gives us 4, 1 plus 4, that gives us 5, 1 plus 5 rather, that gives us 6, and 1 plus 6, that gives us 7. And we do the next 2 plus 1, that gives us 3, 2 plus 2, that gives us 4, 2 plus 3, that gives us 5. So the next step is try to get the outcome of the events present in this experiment of ours. So the first is for us to get the events of sum that are going to be less than 7. What are the outcomes that are going to be less than 7? So we can see that we have some of the outcomes less than 7 to be equals to. We have 6, 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 we have 5, we have 5, we have 5, we have 5, we have 4, we have 4, we have this 4, we have 3, we have 3, and we have 2. So we can decide to extract that out by saying the outcomes that are less than 7, we have them to be equals to. So that's a 6, 6, 6, 6, 6. We have 5, 5, 5, 5. We have 4, 4, 4. We have 3, 3, and then we have 2. And we have a total of 15 of them. So what are the outcomes that are lesser than 5? The outcome that are less than 5. So what are those outcomes that are less than 5? You can see that the outcome less than 5 is going to include 4, 4, 4, 3, 3, and 2. So that means the outcomes that are less than 5 is going to be equals to we have 4, we have 4, we have 4, we have 3, we have 3, and we have 2. So we have the outcome that are less than 7. We also have the outcomes that are less than 5. Paying a closer attention to this, we can see that there's a form of intersection between both events. That is, the outcome less than 7 and the outcome less than 5 have some common element between them, and that we can just write as less than 7 intersection less than 5. And the intersection is actually going to be equals to we have 4, we have 4, we have 4, we have 3, we have 3, and we have 2. And these are the intersection between both events. So let's use our Venn diagram to pictorially represent this question of ours. So we have 2 circles as usual. So let us draw this first circle, and we decide to copy and paste this, and we bring it up here to intersect that. So I will also draw the rectangle to represent the universal set. Okay, so we bring it down here. So the universal set is the rectangle and the circles represents the given set. So what are the intersection? We have 4, 4, 4, 3, 3, 2. So we have 4, we have 4, we have 4, we have 3, we have 3, and then we have 2. So these are the intersection. So we can call this less than 7, and we call this less than 5. So what are the values that are less than 7? We have 6, 6, 6, 6, 6, 5, 5, 5, 5. So we already have 4, 4, 4, 3, 3, 2. So we are going to be having 6, 6, 6, 6, 6, 5, 5, 5, 5. Exactly. And for the values that are lesser than 5, you can see that everything right here is actually inside the intersection, and this is the Venn diagram that represents our question. So for us to get the probability that the value is going to be less than 7 or it's going to be less than 5, we have to get the probability for a value to be less than 7. And for a value to be less than 7, we have how many of them? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that is 15 of them divided by. Now the sample space is the count of all of the sample points right here, and we have that to be equals to 36. So the probability of having a value less than 7 is actually equals to 15 divided by 36. So the probability of having a value less than 5 is going to be equals to, so when we count the values that are lesser than 5, we have them to be equals to 6. So that means we have 6 divided by 36. And when we work on the intersection, that is less than 7 intersection less than 5, so that is also equals to 6 divided by 36. And when we use the addition rule formula for mutually inclusive events, and as we can see, there's an intersection between them, so that means the probability that a value is less than 7 or less than 5 is going to be equals to 15 divided by 36 plus 6 divided by 36 minus 6 divided by 36, and the answer to that is actually 15 divided by 36, which actually gives us 5 over 12. If we decide to convert this to a decimal value, we have our answer to be equals to 0.417 approximately, which is 41.7%. So if we roll 2 fair die at the same time, there is a 41.7% chance that we are going to be having a sum less than 7 and a sum less than 5. So let's solve the next question. So our final question says that for numbers 1 to 9, get the probability of getting a number less than 4 or 2. So the sample space of our experiment, which is going to be S, is going to be equals to 1 down to 9. So we have 1, 2, we have 3, we have 4, we have 5, we have 6, we have 7, we have 8, and we have 9. So the two events we have right here is having a number that is less than 4 and a number that is less than 2. So the number that is less than 4, we can say numbers that are less than 4. We have that to be equals to 3, we have 2, and we have 1. And the numbers that are less than 2, so numbers that are less than 2, we can see that we have that to be equals to 1. So numbers that are less than 2 is just 1, and numbers that are less than 4, we have 3, 2, 1. We can also see that there's a form of intersection between both events. So this is 1 and 1 right here. So that means an intersection that is less than 4 intersection less than 2 is actually going to be equals to 1. And since we have an intersection right here, it definitely means we are working with mutually inclusive events. So let's try to use the Venn diagram. So we have the rectangle, the circle rather. We copy this, and we can also paste it again. So we bring it right here, and we can decide to make it a red marker. So it's time for us to draw the universal set, which is represented with rectangle. So we make that black. Very important. All right, so the next step is for us to fill all of the necessary details. So we have less than 4, and we have here to be actually less than 2. So we start with the intersection, and the common element between them actually equals to 1. So what are those values that are lesser than 4? We have 3, 2, 1. So right here we have 3 and we have 2, and the values less than 2 is just 1, and we have just the 1 right here. So the probability that a value is less than 4 is going to be equal to the number of values that are lesser than 4 divided by the sample space, and the number of values that are lesser than 4 is actually equals to 3. So we have 3 divided by, and the sample space of this experiment is actually equals to 1 to 9, which we have 9 of them. So that gives us 1/3. Let's keep that in mind. So probability that a value is actually less than 2. So we have less than 2 to be equals to number of values that are lesser than 2, which is equals to 1 divided by 9. Very important. And the probability of the intersection, that's less than 4, intersection, we have less than 2, and just only one element is actually lesser than 4, and at the same time lesser than 2. That's going to be equals to 1 divided by 9. So when we use the addition rule for mutually inclusive events, we are going to be saying that probability that a value is less than 4 or a value is less than 2 is going to be equals to, we have 1/3 plus 1/9 minus 1/9, and that gives us 1/3, which is actually equals to 0.333. Converting this to decimal, we have 33.3% chance. If you learned something new and you enjoyed this video, I would really appreciate if you can subscribe to this YouTube channel and give this video a thumbs up. It's going to mean a lot to me. Thanks for making it to the end of this video, and we see you in the next one. Bye for now.